Okay, hi. My name is Marcos Dantus. I'm a professor here at Michigan State University. And the purpose of this video is to address a number of questions regarding quantum mechanics that I have come across ever since I first took my first quantum mechanics class many years ago. And that is that sometimes you take quantum mechanics and there's usually a historical review that can be either extensive, meaning one full class, or maybe even less than that. And you hear things such as the black body radiation or the UV catastrophe, the photoelectric effect. But those topics are covered not in any depth, and you don't quite get the sense, or at least I never got the sense of how does that relate to what we need to learn? How does that relate to the wave function that I need to start understanding? And so I thought that it would be a good idea to do a historical review. And as part of this historical review, I have found some very interesting things, which is that in science, it's not that Schrödinger comes along and says, wow, I came up with this equation that solves all of the problems that we've been having understanding nature, especially as it relates to atoms. The truth is that it's a number of scientists over 200 years that led up to that moment. And so this review kind of, I hope, will give you that sense, right? That it's one scientific observation, if taken to all its implications, then lead to a few new realizations, which again, taken all together, get you to the next better understanding of nature. And so in that sense, this is not a in-depth review of what came before quantum mechanics. It's kind of like putting in perspective all the little pieces of the puzzle. And then if you're interested in any specific piece of the puzzle, then you can go to the internet or to any of your favorite books and find more about it. Okay? So with that in mind, the shorter version of what this video is about is how did we arrive at our present understanding of chemistry, atoms, molecules, and pretty much everything that we can see and touch. Okay. So by the way, how did the concept of the atom evolve, right? Is it more like Jimmy Neutron's type of atom? How do we came up with the whole periodic table? And finally, can we see atoms, right? So here are a couple of pictures. These are individual xenon atoms, and these are carbon atoms that belong to a molecule called pentacene, which has 5 kind of benzene rings. So the answer is we kind of can see atoms, but we need to see now how did we get there, okay? Okay, so the period I have chosen to focus is the period between 1690 and 1939, okay? So I'm not going to go back to the Stone Ages. I'm not going to go back to the Egyptians and all the other cultures, which there are a lot of contributors to what is light and what is fire and things like that. But I decided to start more or less where we have the beginnings of classical mechanics and so on. Okay? And all the way to 1939, once we've solved the Schrödinger equation and we kind of figured things out. And I'm going to be using a number of color codes in this summary. Yellow would be kind of things related to light. Light as a wave, as a photon, and containing energy and traveling at the speed of light. Experiments on electrons, because people had no idea that electrons existed, let alone what they are and how they behave. The nuclei, interactions between light and matter, and certain experimental problems that were pivotal that we just could not understand. Okay, so here's the summary. And if you have any questions, just send me an email. Well, of course, now I'm going to go through this summary. As you can see, there's a lot of topics. And even as I was preparing this summary, I came up with a few new little details that would be useful to explain. Okay, so let's start with, by the way, I don't know the precise pronunciation of many of these last names, so please don't fault me for that. I would say that Huygens, okay, in 1690, was wondering about the nature of light, and in particular, he had these crystals of this mineral called calcite, and he noticed that light can travel seemingly at two different speeds, and he was trying to understand how that happens. And through his observations of how light travels in calcite, he came up with the idea that light must be a wave. And these findings in 1690 were greatly overshadowed by Newton, who was quite a very important physicist in this world. And Newton said, no, light is composed of particles. And so starting Newton's statement that light is really particles, it took many, many years before anybody would consider light as a wave again. Okay? Now, very important contributions of Newton are classical mechanics, right? So force equals mass times acceleration, momentum equals mass times velocity, kinetic energy equals 1/2 mv squared. And something that's going to be very important for quantum mechanics is going to be circular motion. So if something is spinning, do we use the same equations? And it turns out that the equations are very similar, but now the mass is going to depend on something called the moment of inertia. Okay, so for example, it's not the same for me to spin this way as it is to spin this way, right? This way has more inertia than this, and this can be quantified by the moment of inertia. So we have I equals r squared m, and that would be the mass and the spacing between the masses, for example. And then we have instead of linear momentum, we will have angular momentum, which is the big L. Instead of force, we will have torque. So you can see F equals ma and torque equals I alpha. Very, very similar equations. And then the kinetic energy will be 1/2 I omega squared, where omega is the angular velocity. Okay? So very similar equations, but applied to objects in rotation. So we had this, more than 200 years before quantum mechanics. So in principle, we could have calculated a lot of things, but those calculations were not making sense. Okay. Another very important contribution is this idea of quantization, right? Somehow, when we're studying quantum mechanics, we learn about quantization as if it's the biggest surprise ever. Like, can you imagine the energy levels were quantized? But turns out that a long time before, in 1756, we had already learned about quantized energy levels. And that's work by D'Alembert and Euler later that studied string instruments. Okay? And in string instruments, you have what is known as harmonics. So here you would have a certain note. And then if you put your finger very tightly, then you only get this motion. But if you put it lightly, then you get this motion. Okay? And that would be the second harmonic. And so on, the third harmonic, and then the fourth harmonic. And what's interesting about this is that the energy is quantized. Furthermore, we see nodes. right? So the second harmonic has one node, the third harmonic's two nodes. All of this is something that is going to come back in quantum mechanics, but it should not be a big surprise. If we make a system that is analogous in quantum mechanics to what a string would be, meaning one-dimensional, we should see the same results, provided a few things we learn later on as we learn in quantum mechanics, all these pre-observations to quantum mechanics. Okay, so now, notice the nodes and the oscillations of the string. Okay. And the frequency of string instrument is quantized. That's the big conclusion here. Okay. One of the characters that was not introduced in my quantum mechanics, but should be, is Benjamin Franklin. Okay, Benjamin Franklin, who was quite a character and had tremendous contributions in all sorts of things, especially government of the United States. At some point, he decided that he was done working for the United States and working for, all these official roles. And he said, I'm just going to dabble a little bit in science. And he had some major contributions. And one of his major contributions is that electricity involves the flow of particles. And not only that, but that there's positive and negative electricity. You see, before that, we did not know that, and he actually made the connection that lightning, which, if you remember, thousands of years ago may have been the gods being mad or something, was just identified as electricity and electrical flow, and that you could make it flow away from the building and not have the church or whatever taller building in the little village burned down. Okay. And then from Coulomb, we learn about the attraction between opposite charges. And this attraction has a 1 over r squared dependence. Okay? And so we get these kinds of curvatures, which will be very important whenever we deal with quantum mechanical problems that involve a positive and a negative charge, like an atom. So Coulomb, we knew this. 1784 is still, almost 150 years before quantum mechanics. Okay. The next step is the final demonstration that light is a wave. Okay? So when light is a wave, we have something that is very important, and that is constructive and destructive interference. Okay? When we have constructive interference, we have the brighter spots here. When we have destructive interference, we have the darker spots. So when we have waves, we get harmonics, we get quantized energies, we get nodes, and we have constructive and destructive interference. All of these elements are going to be very, very important for quantum mechanics. Okay. Next, we have something that was called cathode rays. So you would connect a negative charge and a positive charge, and they would in vacuum, but the vacuum was not perfect. And if you had a discharge, there would be kind of like a little lightning rod, and you would have this flow of electrons. You would have light being emitted, but they did not know exactly what this was. But at least they saw these cathode rays. And these cathode rays, because they're made out of electrons, which they didn't know that it was electrons, but they could put a charge here and they could deflect going up and down. And here, I'm going to talk about something fascinating about science. Once you discover something, you can begin to say, okay, can I use this for something interesting? If I can shoot electrons and I can make them go anywhere I want, I can make a screen and put a phosphor and then write things on the screen. And yes, that's the preamble of the CRT or the TV, right? And these TVs are function by shooting electrons at the screen. And if that is the case, if you put a magnet on the screen, you get some really cool patterns. However, I doubt anybody watching this video anymore has those kinds of TVs, but if you happen to have one and you do that, you're going to magnetize the screen and it will forever look like this unless you demagnetize it. Okay, you demagnetize it by moving the magnet randomly until you shuffle the spins on the surface. And I've done it, and I was really worried about how am I going to explain that I ruined the TV, and then I had to demagnetize it and save my skin. Okay. One of the problems of quantum mechanics that is important to understand is black body radiation. Okay, and the first I heard about black body radiation, I was like, what do you mean a black body? Can this be a black body and can this radiate? No, what we mean is that anything that is hot emits photons. So something that is really hot, like this lava flow, is very hot, and so at night you can really see a lot of light being emitted. Okay, and so the question was, people started making spectrometers, so spreading out the light and seeing what colors were inside. And what they found was that in terms of wavelength, you would see, this kind of curvatures. And the classical prediction was that the amount of light would increase and increase and increase, and you would have an infinite amount of ultraviolet light. But ultraviolet light seemed to be missing here. And so this was known as the ultraviolet catastrophe. Now, one of the things that I'm very much in favor of is not using wavelengths for spectroscopy. And the reason is that, as we will learn later, different colors of light have different amount of energy. And so energy is the unit we should be using. And if we use energy, these same plots now look like this. So more energy in this direction, less energy here. And now what we see is that as we increase the temperature, we are getting emission with higher energy. Okay? And there doesn't seem to be any catastrophe in this plot. But there's a question from the audience. Yes?
For the classical theory, what was the thing that went wrong? So were they thinking of it as waves and just photons? Or what was...
Right. Okay. So the question is, why was classical theory predicting that you would see more and more light at essentially all wavelengths, or that it would keep increasing? And what was happening, as we will see later, is that the carriers of light, or there's these particles that are about to be discovered in our timeline, carry a certain amount of energy. And so that was nowhere being taken into account. So if the classical theory was fitting these curves, there was no reason why this curve would stop. However, if you think that light travels as particles of a certain amount of energy, then to conserve energy, if you had one photon with a lot of energy, then you had to have very few of those. And at some point, you couldn't have photons with infinite energy. I mean, those cannot exist. And so that's what was causing this to miss. But it took a long time for people to figure out, and we will see how that was figured out, which, again, the explanation I heard before was that, well, Planck came up with this formula that he didn't like, but it solved the problem. But what I never learned was, yes, but how did Planck come up with that formula? And we will see that. Okay.
What have we learned in part 1? We've learned that light, through experiments, shows interference. Therefore, it shows wave behavior. We learned from the classical wave equation that string instruments, for example, have quantized or discrete momentum and energy levels. That electricity and magnetism are related. Electricity involves flow of positive or negative particles, which attract or repel each other with an inverse distance square dependence. That electrical particle beams can be manipulated with the charged plates or magnets, and that hot bodies emit light with a spectrum that cannot yet be explained. In the next section, we will learn about a set of equations that unites electricity, magnetism, and light. We will learn that chemists were busy creating the first periodic tables based on a concept of valence. Note that in those days, they were not talking about valence electrons, they were talking about equivalence. Basically, one equivalent of oxygen for two equivalents of hydrogens made water. We will learn that Boltzmann's thermodynamics laws of gases imply that gases are made out of atoms or molecules and that these have discrete energy levels. We will learn that atoms are found to emit light or absorb light at very precise wavelengths, that electricity and light are experimentally related, and that the speed of light is found to be constant, independent of the direction and the speed of the emitting object. So, see you in part 2.